Okay, it's 11:05 now, and today we are going to discuss Module 9. And Module 9 is about analysis of kinematically indeterminate pin-jointed frames. We'll be discussing the trusses with the help of Stiffenes method. So this will be the topic of discussion. Remember, its analysis is just like the way we did beams and rigid joint frames. The only thing is we are assuming pin jointed connections, so it will not be having fixed end actions. So our AML matrix is going to be 0, and similarly, well, we will go through the one by one through all this discussion. Topics to be covered will include introduction, prerequisites for using stiffness method for trusses, kinematic indeterminacy of trusses, stiffness method procedure for truss analysis, procedure of computing stiffness matrix in local and global coordinates, analysis of trusses, problem 1, 2, 3, and 4 problems we will be discussing. Introduction. Trusses are analyzed with stiffness method due to, again, because of those three reasons. It's systematic. You can find out the support reactions, and you can find out the member forces also. And in this case, we will be having the axial forces now in the members. Now, about the method, the basic method for the analysis of indeterminate truss by stiffness method is similar to indeterminate beam and rigid frame analysis discussed in the previous lessons. However, fixed end actions, as I said, are not taken in order to have simplicity in the structural model. Determine the degree of kinematic indeterminacy of the structure and then analyze the structure. So this is going to be the procedure. Prerequisites for analysis with stiffness method, again, 3 things you must know. One is enough concept of matrix algebra, must be able to find the kinematic indeterminacy of trusses, and enough concept of trigonometry. Now, kinematic indeterminacy of trusses we are going to discuss because this is going to be the base for this method. So, the truss is said to be kinematically indeterminate when the total number of degree of freedom at joints exceeds the number of reactions forces. What does this mean? At each joint, if we have reaction, it means it will not be allowing in that direction the displacement, so the kinematic indeterminacy will be 0. But if there is no reaction, so then we will be having the degree of freedom at that particular location, and we count that for a structure now, and that gives us the total kinematic indeterminacy of the structure. Now, in 2D trusses, at each joint there are 2 degrees of freedom. Now, each joint can give you 2 degrees of freedom. One is horizontal translation and one is vertical translation. But joints where supports are present reduce the degree of freedom according to their nature at that joint. Roller support can restrain only perpendicular settlement to it, and hinge support can restrain both. Hinge, why it can do both? Because in both directions it can provide the reaction. So it is not allowing the freedom. So it means at hinge it will be 0. If it is a roller perpendicular to the plane on which it is resting, it can offer the resistance, means displacement in that particular direction will be 0, but in other direction it will be allowing the rotation. So for 2D trusses, simply now kinematic indeterminacy is becoming equal to twice the number of joint, twice from the where this 2 is coming, these are the 2 displacements per joint, and minus the number of reactions. So kinematic indeterminacy is equal to 2J minus R, where J and R are the number of joints and unknown reaction components respectively. So very easily by applying this equation, you can find out the degree of kinematic indeterminacy, 2J minus R. Now, how we find out with some examples now, let's explain this process now. Now, this process given A, B, C, D, E, and F. So it has 6 joints, number of members you can count, and find the kinematic indeterminacy of the truss shown in figure. At A, we have a hinge support, and at D we have a hinge support. So now if we start now counting the number of reactions, so 2 reactions we have at A and 2 reactions at D. So the number of reactions now in this structure are 4. Number of joints now A, B, C, D, E, and F, these are the joints shown is in yellow color. So 6 joints we have. Equation we discussed, kinematic indeterminacy is equal to 2J minus R. So 2 times joints are 6. So 2 times 6 minus number of reactions are 4. So this is 8 degrees of kinematically indeterminate structure. And where are those 8 degrees now? 2 we have at joint B, horizontal and vertical displacement. At C, similarly horizontal and vertical. At E and at F also horizontal and vertical. So those free joints are giving you 2 degrees of indeterminacy each. 4 joints are free. So 4 times 2 is equal to 8. So 8 degrees. This is the kinematic degree of indeterminacy of this problem. Another now structure is shown. Find the kinematic indeterminacy of the structure shown. Now at the left side, if you see, a roller support is given. At the bottom, a hinge support, and then at the right side, a roller support is given. So number of reactions now, roller and roller. So we have 2 rollers now. So 2 reactions we have from these rollers and 2 from this hinge now. So 4. So R is equal to 4. Number of joints we have 4. These yellow are the joints. So now kinematic indeterminacy, again, if you apply that equation, 2J minus R, so 2 times 4 minus 4 is equal to 4 degrees. And which one are those 4? Here it can slide in the vertical direction about this roller. Here it can slide in the vertical direction, so displacement in the vertical direction. The top one, which is a free joint, so it can move to the right, left, right, and it can move in the up-down direction also. So means it is 4 degrees indeterminate. Now analysis procedure we are going to discuss, and this is easier as compared to the beams and the rigid joint frames, and the reason is that we don't have ADL matrix here and we don't have AML matrix here. So it is easy to find out the unknown joint displacements, and it is easy to find out the member forces also. Now, the basic method for the analysis of indeterminate truss by stiffness method is similar to the indeterminate beam and rigid frame analysis discussed in the previous lessons. However, fixed end actions are not taken in account to have simplicity in the structural model. negligible. Those fixed end actions are negligible. Why? Because when we have a bolt connection or a rivet connection, what happens? You may have a slight fraction there which can resist negligible amount of movement, but we ignore that case and we say, okay, now the moment taking capacity of this joint, it is fractionless and it is zero. The basic equation was, this was the equilibrium equation, AD is equal to ADL plus S times D. But in trust, what we do, fixed end actions are equal to zero, so we put ADL is equal to zero. From where this ADL was coming? When we have a fixed ended beam under the actual loads, and we find out the member end actions. That was the ADL matrix. So when this ADL matrix we take equal to zero, this equilibrium equation reduces to AD is equal to S times D. Similarly, for the member end actions, what was the basic equation? The typical equation was AM is equal to AML plus AMD times D. But AML now will be equal to zero, so AM will become equal to AMD times D, which is written here. So AM will become equal to AMD times D. Now, computation of stiffness matrix, we will discuss how we find out the stiffness matrix here. The stiffness matrix computation in truss analysis is the key to analysis. The stiffness matrix may be stiffness matrix in local coordinate system and structural stiffness matrix in global coordinate system. What is a local coordinate system and what is a global coordinate system? Now, local coordinate system is in which we take x-axis along the axis of the member, along the length of the member. That is becoming our x. So when the member orientation is changing, the local axis is also changing. So for different members, we have different local axes. For each member, we have a separate local axis, and perpendicular to that, perpendicular to the length of the member, we have the y-axis of the member. Global coordinate system is what? In this case, pure left-right horizontal, that we take as a global x-axis, and perpendicular to that, which is vertical, we take that as y-axis. So that is the structural axis or the global coordinate system. Now, structural coordinate system or global coordinate system, we'll discuss this in a moment now. Now we can explain these things. You see the same truss now which we discussed to find out its kinematic indeterminacy. It's a kind of different one because we have a roller support here, but the configuration is almost the same. Now in this green, now you see member 1, 2, 3, 4, 5. These are the member numbers. Now just to describe now the local axis and global axis concept, this orange member is shown here, which is member 7. So for this member 7, its local axis will be along the length of this member. So that will become our XM now. M is for the member axis. And perpendicular to that, that will become our y-axis, local y-axis, which we will represent by YM. Member axis or local axis. If we take this diagonal, this red one, so local axis will be along the length of its member, and perpendicular to that, that will become our y local axis, YM. Now we will be developing a relation also, but let's now go to the very basics now. This is joint J of member 7 and this one is joint K of member 7. We discussed the local axis. X-axis is along the length of this member and perpendicular to that we have y-axis. The global axis you see at the bottom here, along the x-axis we have this x. So this is the global coordinate system, this x-axis, and along the y-axis, this is y-axis. Now, when we solve this problem, all these local axes that they must be transformed to standard axis, which is the global axis or the structural axis, which is shown at the bottom now. Now we are discussing this orange one, member 7. Member 7, this is the origin of the global axis, this x and y, this intersection, this is the origin. And joint J of this member 7, it is located at xj. And the far end, which is joint K, it is located at xk. X, which one x? We are taking this in the global axis system now. So the horizontal projection of this member 7 is becoming now xj minus xk minus xj, which is written here. This is the horizontal projection of this diagonal member 7. Vertical projection, if we see, so the vertical projection again from the origin, these distances are given. You see the yj up to here, and you see yk, which is up to here. So the vertical projection from here to here, this is the vertical projection of this member 7, which is yk minus yj now. We can apply now a trigonometric function to put this theta in terms of these coordinates. Now, what is this d1 and d2? These are now the displacement in the horizontal and vertical direction at joint J, and this d3 and d4, the displacement at K in the horizontal and vertical direction. So horizontal followed by the vertical, horizontal and followed by the vertical. And which one displacements? They are in the global axis system, in the structural axis system, not in the local one. In the local one we will discuss now. Now let's how we put this theta in terms of, so trigonometric functions we will be bringing in. Now this is the same member 7 now, which was inclined joint J, joint K. You see here xk minus xj, which is the horizontal projection of this diagonal member. And the vertical projection you see here yk minus yj. This is now the local axis system. Here you see x-axis of member axis, and this is y-axis of this local or member axis is the same now. So here you see for the member x-axis and its y-axis. This is local axis system. And here this one horizontal and vertical, this is the global axis system now. Now if with the global horizontal axis, if the member is making an angle theta in the counterclockwise direction, so this angle theta we can express in terms of these coordinates now and in terms of the length now. What will be cos theta now? Cos theta will be base divided by length of the member. And how much is the base now? It is xk minus xj. How much is the length? It is L. So xk minus xj divided by L. Cos theta is equal to xk minus xj divided by L. What about the sine theta now? Sine theta will be perpendicular divided by the hypotenuse. Perpendicular is how much in terms of the coordinates? It is yk minus yj. So sine theta is equal to yk minus yj divided by L. So now we will be developing a relation actually, and from here now onwards, you know that what is the global coordinate system, what is the local coordinate system. Now with respect to which one axis we are measuring this theta, and what is the cos theta in terms of the coordinates and length, and what is the sine theta in terms of the coordinates and length. And here you can see the local axis system and the global axis system also. Next now, here now, computation of stiffness matrix S. So we have isolated member 7 now. This is member 7 now. If we are developing stiffness, this coefficient matrix in the local coordinate system, so what will we do? First, we give along the x-axis at this J1. Here you see DM1, displacement and member axis 1 now. What is that one? This was the x-axis, if you remember, along the length of this member. So we gave along the x of the member this displacement in M1 direction and find out the member end actions produced. And there, those member end actions will give you the first column of this local stiffness matrix. This will become the local stiffness matrix. Second, what we do, rest of the positions will be logged. Only displacement will be given in this DM1 direction. D is for the displacement, M is for the member axis, and 1 is for the direction 1. So DM1 is equal to 1, and we give DM2 is equal to DM3 is equal to DM4 is equal to 0. Second step, what we do, DM2 we keep equal to 1, and DM1, DM3, and DM4 we keep equal to 0, and we generate the second column of the local stiffness matrix. Similarly, DM3 is equal to 1, rest 0, and then DM4 is equal to 1, and we produce this turn by turn third column and fourth column now. This was the story for the local displacements now. What about the global displacements? Here at joint J, horizontal displacement, this is the global direction now. So this we call D1 and the vertical we call D2. Here at joint K now, the horizontal displacement D3 and the vertical displacement is D4. Rightward and upward we take positive now. And these are the degrees of freedom also. So when we give horizontal and vertical, this will give you the structural stiffness, which we call the global stiffness matrix of the structure. Global, why global? Because we are giving now displacements in the global direction, which are horizontal and vertical. So we will develop now turn by turn these elements now. S11, you see the configuration of the structural stiffness matrix also. Why 4 by 4? Because the degree of freedom of the member is 4. How 4? 2 at one end and 2 at the other end now. In the local axis, it is along the length of the member and perpendicular to this length of the member. And in this global axis system, we have horizontal and vertical and horizontal and vertical. These are the degrees of freedom now. So now, let's computation of stiffness matrix in the member or in local coordinate system. Look, local, again I'm saying local and member axis, it is the same now. And here you see, this is the x-axis along the length of the member, and perpendicular to this, it is the y-axis. This is the local axis system now, which is also known as the member axis system. Now, DM1, this is along the axis, and DM2 along the y-axis, DM3 displacement along the x-axis, and DM4 along the y-axis at the other end. These are the displacements now. Turn by turn now, we will start giving the displacements and logging at the other locations, and we will produce the stiffness coefficient. We will compute the stiffness coefficient values. This is now when we provide DM1 is equal to 1. So computation of stiffness matrix in the member or local coordinate system now. What we are doing now, this is the original position. Now along the DM1, what we are doing, we are providing this delta is equal to 1 now. So from here, this member is sliding in this direction and it is coming here now. This roller is shown along the x-axis now. So now how can it roll this point to here when we start pushing it? Compression. So how compression is shown? Compression is shown by this direction now. This is producing compressive force, and this is also producing now to balance this. You see here now what we are doing here. This is a hinge support now. It cannot move in this direction. It cannot move in this direction. So we provide a hint. So this end is locked now, and here we are only providing now in the direction of x-axis. So this roller guide is provided. Why this is now towards this member? The reason is that it is shortening, and shortening is always due to compression now. So this is why this member we are shown by compression. These two arrows are looking at each other. Now, if you remember, delta is equal to PL divided by AE, a very famous relation which we have from the for the axial forces. It is giving you the delta relation to the force applied. Now, delta, what we do now, we provide delta is equal to 1 now. Unit displacement is provided. So if we put this equal to 1, so then P is becoming equal to L over AE now. So you see here, this is EA over L now. And this P will, this P will be the stiffness coefficient S. Why? Because this is because of the unit displacement now. So here now, let me get my call for a second.